So hi and welcome back to Roy's Desk. I'm back with another new video, another new project as well, a new journey where the destination is a THD or a distortion measuring setup for amplifiers. And this video is all about how to design an audio oscillator. If you don't know what I'm talking about, then more on this in the video. But these two are the circuits for the audio oscillator, a very low distortion audio oscillator close to 2 ppm, and this time I have used mostly all the SMD components. So this project is definitely going to be a challenge for me because I have never designed this before and there are very less information on this in the internet also about the DIY part. I have created a playlist and there I will put all the videos in this series and we will talk everything in detail about this project. So without wasting any further more time, let's get started. Okay, so before understanding this circuit, we need to know why do we actually need this. The why question always comes first. And in order to address this why, we need to see where exactly we are going to use this circuit. So if you have seen my previous videos, you will know that I have already tested this amplifier circuit in here. Tested the power output of this amplifier circuit in here. And what we do for testing the power output is we measure the peak to peak swing of the output of the amplifier by feeding one input signal, and we measure the wave in our oscilloscope in the time domain. This is very important because we measure this sine wave, the output sine wave of the amplifier in time domain. Even if the wave that you are getting, even if the signal that you are getting in the output of the amplifier is a very clean sine wave, that doesn't prove that it's a very good amplifier or very low distortion amplifier. What it just proves is that it's outputting a proper sine wave. Now in order to see that if your amplifier that you have designed is actually very low distortion, and if you want to see what is distortion, let us first talk about what is distortion in amplifiers. We are seeing this wave in time domain. What happens if we do that in frequency domain? So suppose the frequency of this is 1 kilohertz. So what we are going to see in frequency domain is, here we measure in dB. We will see one fundamental of the signal which is exactly at 1 kilohertz, and then depending on how the harmonics are there, we can understand if the signal is clean or not. Ideally, if you say 0% distortion or 0% THD, then we are saying that there are no harmonics. There are no second harmonics, third harmonics, fourth harmonics. There are no harmonics in the frequency domain. So in that way, it's 0% THD, which is impossible. Normally what we will have is, we'll have one harmonics at 2 kilohertz, which is second harmonics, then third harmonics at 3 kilohertz, then fourth at 4, then fifth at 5th, and it will go on. And these are harmonics because these are related to our fundamental. Because if you see, its second harmonics is multiplied by 2, this is multiplied by 3, this is multiplied by 4. So these are all harmonics of this signal. So when we say that we are having a 120 dB minus 120 dB amplifier, which means that the distortion caused by the harmonics is 120 decibels lower than the original audio signal. So what I mean is, say this is our fundamental in here and this is at 0 dB in here, say. So the second harmonics that we will see in here is going to be in this place, which is minus 120 dB. So you see, it's 120 decibel lower than the original audio signal, which is in here. And if you want to convert this minus 120 dB in percentage, or because we will see in our datasheet THD will be in percentage, it's a very simple formula. So we will put 10 to the power THD in dB, that is minus 120, divided by 20 into 100 because of the percentage. So it will come like 10 to the power minus 6 into 100, which is equivalent to 0.0001% THD. There are other methods of measuring THD and the values will differ in that case, but here in amplifier we will always measure with the amplitude of the fundamental compared to all the harmonics. And this is how we can say that how clean our amplifier is. Like in the data sheet of LM3886, you will see a THD parameter written. Same goes for any other chip amp, and that will differ depending on the components that you will use for making the amplifier. So if I consider this amplifier in here, the choice of the components will also affect the THD performance of this full circuit board. So after designing a certain amp, we should always measure the THD parameter. Then only we can say, okay, I have designed one clean, low distortion audio amplifier. And this is what we are going to do with this small circuit board. I mean, this is a part of that measurement of THD. So now I'm going to talk about what my plan is of measuring the THD of amplifiers. Now, another question comes that whether or not we can buy something like that which can measure the THD parameter of an amplifier. Well, there are certain devices which measures the THD parameter of amplifiers, but it's really very costly. There is something like this that John Audio Tech also uses, which is very costly again, and it's not possible to bring in India considering all the shipping charges and customs and everything. So the only thing that is remaining now is DIY, and it's a very common thing to measure the THD parameter of an amplifier using our laptop and ARTA software by using one sound card. And if you have seen my previous YouTube shorts, I have shown you that I'll be using this sound card in here. This is a 16-bit sound card. Now there is obviously another question which will come to your mind, that why not our oscilloscope? Our oscilloscopes, if it's having a fast Fourier transform math function, FFT math function, it can actually measure the signal in frequency domain. But the problem comes here is that it's only 8-bit, which cannot go down to a very low value. So basically you see a 8-bit oscilloscope can only measure to minus 50 dB or 0.3% THD, which is definitely not going to be sufficient for our, say, LM3886. It cannot measure the LM3886 distortion figures, and I know there are oscilloscopes which are 12-bit or 16-bit, but the problem with that is that it's very, very expensive. Now the only thing remaining is that we are going to have our amplifier in here, and that is going to provide the output sine wave, which is going to be attenuated down, I will say AT or attenuator, because obviously I cannot use my sound card directly to the output of this amplifier, which will just burn the ADC inside the sound card. And then this attenuator will pull the signal down to say 2 volt RMS, and then comes our sound card in here. This is a 16-bit sound card, and this will feed that signal to our ARTA software, which is having the THD math functions and all, which will directly give you the THD value. This is a 16-bit, can measure very, very low distortion figures. But what about the signal that we are going to feed inside this amplifier? You will basically measure the input signal which is already distorted. Suppose you are using one function generator. Function generators will have a typical 0.1% to 0.3%, because function generators are not only for audio range or audio spectrum frequencies. It has to go to megahertz, and some function generators also needs to go to gigahertz range. It's having many other use cases. So we cannot use a function generator in here, because that if that signal that is coming in here is already 0.2 to 0.3% distorted, then after the amplifier it amplifies it and it becomes still 0.02, because this itself won't introduce any more distortion to the circuit, maybe a little bit, but it will be a 0.2%, and what you will measure through our sound card will be again 0.2 to 0.3% distortion, and you will say, okay, my amplifier is producing a 0.2 or 0.3% distorted sine wave. But that won't be a proper test. So in that way we come to our star of the show, that is this one, which is the 2 ppm low distortion audio oscillator. Now this feeds that to the amplifier, it amplifies the signal, and it will have its own, suppose I'm just saying it will have some 0.01% distortion, this LM3886, or maybe lower, and then it goes to the attenuator, which brings the voltage down or the amplitude or the VRMS down, so that it can be given to our sound card, and that goes to our laptop, which is having ARTA software, which can measure the THD of this amplifier. And now I'm going to explain how the circuit works. So the Wien Bridge or Wien Bridge however you want to pronounce it, is kind of an oscillator circuit, and it is a harmonic oscillator because it produces a sine wave. And the heart of the circuit is the op-amp in here and the RC network right in here. It's called Wien Bridge, by the way, because you can arrange this same circuit in this way. And if you have seen Wien Bridge and other circuits, then you will know that this is a bridge configuration, and that's how you can basically replicate the same circuit right in here. That's why it's called Wien Bridge. But for now, we'll just concentrate on this circuit. So we can simplify the circuit by saying that this is one high pass filter right in here, and this is one low pass filter, this part, and together they form one notch filter where the response will look something like this, which is tuned at a particular frequency in here, FR, which is also the resonant frequency. So ideally what happens in Wien Bridge is that this resistors are same and these capacitors are same, forming a very simple equation for the resonant frequency, and that is FR is 1 by 2 pi RC, and this is also the oscillating frequency of this circuit. So by this calculation we can calculate at which frequency the sine wave will be produced, and in other words, if you will say that it is a notch filter and it will only allow this particular frequency to pass through it and it will minimize all the other frequencies, we can say that V out divided by V in is equals to 1 by 3. Now I am not going to detailed calculation, there are definitely videos in YouTube for that. I am only telling you which all calculations are important to understand this circuit. So whatever frequency it's producing, at that frequency the ratio of the V out to V in is 1 by 3 right in here. And definitely we can calculate everything by saying that this is say Z1 and this is say Z2, and we can also say that this is equals to Z1 divided by Z1 plus Z2. Then you can definitely calculate everything with this. Now this ratio can be also called feedback fraction. Feedback fraction is also referred as beta. Now if we say that the gain of this part of the circuit is A and the beta we know is 1 by 3, it will only oscillate if A multiplied by beta is equals to 1. So this is where the main complication of the circuit comes, that when A into beta is equals to 1, then only we will have a sustained oscillation and a clean oscillation. Now one big question arises after these calculations, that we know that A into beta is equals to 1, and we know that if it's 1 it will sustain the oscillation, but what will start the oscillation? The circuit, we are not giving any input to the circuit, right? So there won't be any oscillations. If it cannot start by itself, you have to switch on the self of the car, then only the flywheel will rotate with the self motor, and then only the other functions of the car will start with the timing belt and everything. So what is our starter switch in here? For the oscillations to start, this product and the overall gain of the circuit needs to be greater than 1 at first, then only it will start oscillating. Then we need to make it equals to 1, then it will sustain the oscillation. So now we know if A multiplied by beta is greater than 1, it will start oscillating and it will saturate to the supply voltage rails in here, and if it's lesser than 1 it will dampen out, and if it's equals to 1 it will sustain this oscillation. So you can see that how narrow the band will be for adjusting the oscillation, and how critical this point is, that it should be exactly equals to 1, then only the oscillations will sustain. But in order to start the oscillation we need to have it greater than 1. Now there is another question definitely which will come, that okay, we are saying that if it's greater than 1 the oscillations will start, but then again how will the oscillation start is still not clear, right? Because see, when you are saying this circuit will oscillate, but what must cause the oscillation? The answer is thermal noise. So when we switch on the circuit by giving plus V in here and minus V in here, then at first the circuit will have a noise like this with various frequencies. Now you will see it will have a feedback that will be coming like this, and since this is a notch filter, it will only allow a certain frequency, that is our resonant frequency FR, to pass through this circuit and go in here, that is VF, V feedback. From this noise we are only sampling out a particular frequency, that is FR in here. So FR will be coming and appearing in here, and then we'll have a gain greater than 1 at first, so it will oscillate now, and it will oscillate at a particular frequency, that is FR. So it will try to oscillate close to the rail and until it saturates, but then we will automatically make this overall gain of the circuit as 1. Then it will automatically be sustaining the oscillation at a particular point, and this is how the circuit works. I hope it's clear. First noise, then from the noise it will only sample out a particular frequency, that is our resonant frequency. It will give that to our op-amp. The op-amp overall gain of the circuit will be A multiplied by beta, that is greater than 1 at first. So it will start the oscillation and it will start on increasing, but then we will automatically make this A multiplied by beta is equals to 1, and it will sustain the oscillation. Now the question comes, how are we going to make it greater than 1 at first and then equals to 1 automatically when the oscillation starts? And that is when a very important concept comes, that is not only for this oscillator circuit but are used in a lot of circuits, that is AGC, automatic gain control. And normally the best way is to have one JFET in here, and the easiest way is to have one lamp in here. So with this we can control this circuit dynamically, and there will be obviously a control circuit in here which will control it depending on the output. There will be a feedback path which will have a control circuitry which will feed this JFET. Okay, so after understanding what is a Wien bridge, I started digging around the internet and I could find some good DIY open source projects. The best one is the Victus oscillator. If you search Victus oscillator 1 kilohertz, you will find this link. If you click on this link, it will show you one project which uses this Victus oscillator right in here. Now, best part is that you can order this Victus oscillator if you are US based, and if you search more, you will get this page, Tolis DIY, which uses a Victus oscillator to make a DIY audio oscillator project. You can go through this link. I will definitely give that link in the description. And this is the circuit. So as you can see, it uses one JFET to control the gain, and also this is a part of the AGC or automatic gain control, and this is tuned exactly at 1 kilohertz. And the next one is this oscillator, Akitika. I don't know if I am pronouncing it right or not, but this is another one. And the good thing about both of this, the Victus oscillator and this one, is that you can buy both of them. And considering the thought process that went into the project, I think this is a pretty reasonable price that they are offering. And if you click on this link, which is this PDF, you can actually download the full project. This one is featuring the easiest circuit, because if I show you the circuit, it's this one. So it's featuring one lamp to control the gain, or the lamp is the part of the AGC, unlike the complicated circuit for the JFET. This uses one lamp. This is the easiest form of Wien bridge. You can get more details about this circuit in this PDF only. If you could find this type of lamp, then I would suggest this is the best and the easiest one with least amount of complexity in the circuit. If you go back to the website, you can see that they also have the full project details, and you can see a video is also there in the YouTube. And the best part, they have shown how to build the attenuator also that comes before our sound card. So this is the document which features the attenuator. Now I am going to follow the same circuit that they have used in here for my attenuator also. And now comes the circuit that I am using, which is this one right in here. I think it's pronounced as Janus card. So if you go inside the document, this is the thing that I am going to use. But yeah, definitely I'm not going to use this circuit right in here, because this is for minus 140 dB audio oscillator. The best part about this document again is that definitely it explains each and every aspect of the circuit, how it's designed, how all the components work. But that's not the point, because now they have also given us a simplified version of the circuit. So it features one LCR in here, which is our gain control unit, and this full part with the IC TLO81D is a part of the AGC. I mean, together with the LCR and this op-amp, this is a part of the AGC, or automatic gain control. I'll definitely explain the circuit in a minute. Now, there is another point which I want to mention is that, see, all the components that we're using for this project needs to be very high quality components. I think here also they have mentioned that right selection of passive components in the signal chain is another important requirement for minimum distortion. Resistors are preferably 0.1%, 15 ppm per Kelvin. I'll show you from where I've sourced all the components. Just note this point, that all the components should be very top-notch component, so that the drift is as less as possible due to thermal reasons and all, because this is a very sensitive circuit. So moving on to the circuit that I have designed. So that's the circuit. The main problem with this oscillator circuit is to get the gain controls component. As you have seen, one of them uses bulb, one of it uses JFET, and here they are using LCR. So getting the right LCR is the main thing, and I got this LCR 0202 in robo.in. In fact, I have got all the components mostly from robo.in, because I could get the high quality resistors and capacitors easily in robo. I'll show you the list of the components that I have purchased from robo in a minute. So see, this is the circuit, and here this part, this IC is a part of the Wien Bridge, and this is the negative feedback part. This resistor is going to set the initial gain of the circuit, and this part, as you can see, is for the integrator. Now whatever output we are getting from this U1 or the OPA 1611, now if you are getting any op-amp better than this, this is a extremely low distortion op-amp. This is really very high quality op-amp. If you are getting anything better than that, you can use it in here, but I have used this because I could find this in robo, and whatever output it's giving out, that is getting rectified with this diode in here. And here the TL431 is not used as a shunt regulator, rather is used as a minus 2.5 volt stable voltage. A part of the signal that we are getting in the output, we are feeding the rectified signal to this integrator circuit, which is controlling this transistor in here, and that controls the output of the LED, which controls the resistance of this internal resistor of the LCR. So depending on the amplitude received, it will control the resistance of the LCR. It will be slow, but I don't know how much slow. Initially the resistance will be very high, and as the LED lights up, the resistance will go down, and making the overall gain of the circuit equals to 1, and then the oscillations will sustain. After this, I designed the PCB, and that's how it looks. Now this R7, which is the basically this 10 ohm resistor, which is in parallel with this LCR. This one you can use a quarter watt easily. I was already having this 2 watt 10 ohm resistor laying around, so I just thought that I will use this one, not to waste money on another component, so just use this. But this is how the circuit looks, and if I just switch on both the layers, this is how it looks. Let us see the 3D view. Yeah, that's how it should look. Capacitors obviously will be smaller ones. I just used the same pitch of this capacitors, but yeah, this is how the circuit looks like. Made it as compact as possible to reduce the noise. Used ground plane again to reduce the noise, and after doing this, I went ahead and ordered from robo. So this is the list of components that I ordered from robo. This is our LCR, and this is the op-amp. You can see it's a pretty costly op-amp, but yeah, it is fine. We have to use a very high quality op-amp of the Wien Bridge. This is the TLO81D for the integrator circuit, or also the part of the AGC. TL431, and this is where our resistors will start. You can see it's 25 ppm per degree Celsius, and this is 0.1% accuracy, and mostly I could find each and every component in Robo website. If you can find this component or source this component from any other place where they are cheaper, definitely go ahead. I just got it, I ordered it, and after ordering the components from Robo, I ordered the PCBs from LAN circuits. Now the reason why I always choose LAN circuits for the PCBs rather than Robo is because they are actually manufactured in India. In between, I got one information that they might ship the PCBs from Thailand and they call it their own PCBs. I confronted them via email. I asked them that is it true or not, and this is the reply that I got from them. So for those who don't believe that they actually manufacture in India, this is a reply from them. If you are willing to visit their plant, be my guest. I'm not going to do that. I'm happy with the mail reply only. So I'm going to always order from LAN Circuits because it's made in India. And after ordering the PCBs, I got the PCBs within 1 week or something. Now, I think it's time to wrap up the video at this point because it's already a very long video. Some people really gets bored if the video drags very long, but I can't help. I try to give as much information as possible in my videos so that when you are designing something like this, you don't face any problems. Next video will come very soon where I will solder all the components to the PCBs. I'll show you the PCBs, empty PCBs, and then we will test the circuits. Definitely stay tuned. I know this is a very interesting project. Even I don't know if it will work or not, but this is a challenge. So until next time, please do like, share and subscribe to my channel. I'll see you in the next video. Till then, bye bye.